Imagine a mystery so profound that solving it lands you a $1 million check from the Clay Mathematics Institute. We're talking about the Yang-Mills mass gap. It's one of the 7 Millennium Prize Problems. In our best mathematical models, the particles that hold the universe together should be massless, floating through space like light. But in the real world, they have mass. This disconnect is a reality problem. To understand this, we look at the hierarchy of laws. Newton ruled for centuries. His equations told us how planets move and why apples fall. But at the subatomic scale, his equations fell apart. Enter quantum mechanics. This is a world where particles can be in 2 places at once, and the vacuum isn't empty, but a seething sea of virtual particles, and where everything is governed by probability. Yang-Mills theory is our foundation for the subatomic realm. It's remarkably successful in experiments, yet mathematically incomplete at its very core. Unlike Newton's laws, we don't know why the math allows for a mass gap, the minimum energy required to create a particle from the vacuum. This gap is why quarks stay locked inside protons. Without it, stable matter wouldn't exist. Experiment says it's there. The math just doesn't explain why. Proposed in 1954 by Yang and Mills, the theory predicted massless particles, but experiments showed force carriers definitely had mass. The proof remained elusive. Solving this requires proving a mass gap exists in 4-dimensional space-time. It involves some of the most complex geometry humans have ever devised. Supercomputers use lattice QCD to see the gap clearly. The universe says yes, but it's hiding the why. In math, seeing isn't proving. A solution would explain confinement, why quarks never appear alone, and mark a giant leap toward a theory of everything that connects all of reality. It's the final piece connecting the subatomic world to the universe we touch. That $1 million check is still waiting for anyone who can bridge this gap. Unfortunately, the universe doesn't give up its secrets easily or cheaply. A history of symmetries. Let's rewind to 1954. Chen-Ning Yang and Robert Mills were looking at electromagnetism. Back in the 1860s, James Clerk Maxwell figured out that electricity and magnetism were 2 sides of the same coin. Later, mathematicians realized this worked because of something called gauge symmetry. Essentially, you can change the underlying math of the field, but the observable physics stays the same. Yang and Mills had a what-if moment. They decided to generalize this symmetry. In electromagnetism, the order in which you apply these mathematical changes doesn't matter. It's abelian. But Yang and Mills proposed a non-abelian version. In their version, the order does matter. This created a whole new kind of field where the force-carrying particles, called gauge bosons, could interact with each other. In electromagnetism, photons don't bounce off other photons. But in Yang-Mills theory, these particles, like gluons, are constantly interacting with one another. The problem? In the original 1954 equations, these particles were necessarily massless. This was a huge headache because the forces inside the nucleus of an atom are very short range, which usually means the particles carrying the force must be heavy. For a while, the theory seemed broken. How do you get mass from a theory that demands weightlessness? Physics found a partial solution in the 1960s and 70s. Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that for the weak force, you could use the Higgs mechanism. This process breaks the symmetry and gives particles mass. But here is where it gets weird. When we look at the strong force, the stuff that holds quarks together to make protons, there is no Higgs mechanism. In quantum chromodynamics, or QCD, gluons should be massless. There is no Higgs for them. And yet, we never see a single lonely massless gluon flying around. Instead, they are always confined inside heavier particles. Something in the way Yang-Mills theory works at the quantum level is generating mass out of thin air, or rather, out of pure interaction energy. This phenomenon, known as mass without mass, accounts for nearly all the weight of the visible universe. It means the mass of your body, of the Earth, and the stars isn't just coming from the Higgs boson, but from the frantic movement of gluons. It's a beautiful dance of symmetry and interaction that defines our very existence. Understanding Yang-Mills theory is one of the greatest challenges in modern mathematics and physics. In fact, proving the mass gap is one of the 7 Millennium Prize Problems, worth $1 million. This is the history of symmetries. We'll continue to the next part. The math of the gap. Ready to get your hands dirty with some math? Don't worry, I'll keep the safety goggles on for this one. The heart of the theory is the Lagrangian density, which defines how these fields behave. That F-Munua part, that's the field strength tensor. It's the core of the field's interaction. Because of that non-abelian structure we talked about earlier, it contains a nonlinear term. This term represents the particles interacting with themselves, which makes the math incredibly complex. Now, when we try to solve this for the spectrum of the theory, the list of all possible energy levels, we are looking for the mass gap, symbolized by the Greek letter delta. This gap represents the difference between the vacuum and the first excited state. E0 is the energy of the vacuum, the ground state. It's the absolute baseline of the universe. For the mass gap to exist, delta must be greater than 0, not just close, but strictly positive. This means the lightest possible thing you can create in this universe still has a positive mass. We've seen evidence of this in lattice gauge theory. It's our best window into this world. We use supercomputers to simulate the universe, breaking it down onto a 4-dimensional grid. These simulations consistently show a mass gap, even if we can't prove it analytically yet. For a specific version of the theory, SU3, the gap is about 1.1 to 1.3 times the fundamental scale. But here's why that $1 million prize is still unclaimed. A computer simulation isn't a proof. We need a derivation that shows this must happen within the framework of axiomatic quantum field theory. So, why is this proof so hard to find? It comes down to something called the infrared problem. Think of it like a foggy landscape where you can see clearly up close, but everything far away is hidden. In physics, ultraviolet refers to high energy and short distances, while infrared is low energy and long distances. We've gotten very good at handling high energy problems through a process called renormalization. We even have a property called asymptotic freedom, which simplifies the math at short distances. At very high energies, quarks and gluons actually act like they're free and easy. But as you zoom out, as you go infrared, everything changes. The physics shifts completely. The force gets stronger and stronger. The math becomes what we call non-perturbative. Our usual tricks of using approximations just don't work here. This is where our current tools fail us. But physicists love a challenge. There are some truly wild ideas on how to fix this gap in our knowledge. Some are looking at instantons, special topological solutions that might be the key to the mystery. Others look at the ADS-CFT correspondence, suggesting our world is a holographic projection. This means our 4-dimensional world might be a projection of gravity in a higher dimension. The math is hard, the stakes are high, but the quest to understand the mass gap is just beginning. Whether it's through supercomputers or radical new math, we're closing in on the secrets of the vacuum. Thanks for sticking with me through the math. Stay curious, and we will continue the next part. Conclusion: why the formal proof matters. You might be wondering, if the theory works in experiments, why do we care about the formal proof? Because the mass gap is the secret to confinement. It's why you are made of solid matter instead of just a loose soup of massless particles flying at the speed of light. If we can solve this, we don't just win $1 million, we gain a new understanding of the very structure of space-time itself. We might find a path to a unified theory that finally brings gravity into the fold. 70 years later, it's a reminder that nature still has secrets that can only be unlocked with pure, rigorous thought. So, what do you think? Is the answer hidden in a higher dimension, or do we need new mathematics? Let me know in the comments, and hit that subscribe button for more physics mysteries. Should we tackle the Higgs mechanism next, or the Riemann hypothesis? Let me know. Thanks for watching. See you in the next video.